Hey, welcome back to Graph Theory. In this video, we're going to discuss a question that I was asked recently about the PageRank algorithm for digraphs. We've been talking a little in the last few videos about PageRank. We applied it to a couple of digraphs with 3 vertices. And to briefly summarize what happens in PageRank, we're calculating a fixed point of this function f, which takes an input v, which is a row vector, and the function outputs as plus 1 minus a times v times w. A is a real number from the open interval from 0 to 1, and it's a parameter that we choose. S is a seed vector that we also choose, and it's a row vector with the same length as v. W is the lazy random walk matrix of the internet digraph that we're applying PageRank to. So whichever internet that we're doing PageRank on, it determines some digraph, and that digraph determines W. And the question I was asked is, why do we find a fixed point in PageRank? Why are we looking for a fixed point of f of v equals as plus 1 minus a times v times w? So I want to talk about in this video why we're looking for that fixed point, how it relates to a rank in the websites. So we're going to start out by briefly reviewing the model that's used in PageRank. And that model is a model of a web surfer. We'll assume that this web surfer has a weighted coin. The coin will land on heads with probability A, and it will land on tails with probability 1 minus A. The surfer also has a seed. We'll call that seed S. The seed will tell them to visit website I with probability S sub I. So we can think of the surfer just waking up in the morning, getting on the computer, getting on some web browser, and we'll represent their website at time step 0 with a row vector, which we'll call H. So if every day they always start at the same website, then we'll have the entry in H corresponding to that website be 1, and we'll have all the other entries of H be 0. We could also have a web surfer who likes to start at one website or another, each of them with equal probability. So we would have the entries of H corresponding to those websites both be 1/2, and all the other entries of H would be 0. So we have H, and we also need a rule for how the surfer is going to get to their next website based on their current website. And their process for figuring out their next website, it'll always be the same process. The process will involve the coin, the seed, and W. So we're going to use this row vector V, which was the input to F, and that V is going to have the probability that the surfer is at each website in the current time step. So the length of V is going to be the number of websites on our internet, and the ith entry of V is going to be the probability that the surfer is at website I in the current time step. So the process that the surfer is going to use is they're going to flip that weighted coin, and the coin will either land on heads or tails. If it lands on tails, the surfer will use a lazy random walk to figure out its next website. So in other words, if the coin lands on tails, and V is the vector of probabilities for each of the websites at the current time step, then the probability that the surfer will go to website I in the next time step is just going to be the ith entry of V times W. So we discussed what happens when the coin lands on tails. Now let's look at what happens when it lands on heads. This is slightly simpler. The surfer will just use the seed, and specifically, the surfer will go to website I with probability equal to the ith entry of s in the next time step. And this happens, the coin landing on heads, this happens with probability equal to A. So we can combine both possibilities for what happens with the coin flip. And this gives us that the probability that the surfer goes to website I in the next time step is equal to A times the ith entry of S plus 1 minus A times the ith entry of V times W. And if we combine all of those entries together, we can see that the vector of probabilities for each website on the next time step is just AS plus 1 minus A times V times W, assuming that V is our vector of probabilities for the current time step. So we have that starting vector H. We can apply our rule for going from a current website to a next website, and we can apply it starting at H. So the vector of probabilities for the surfer's website at time step 0 is H. We're going to take our function f of v and we're going to plug in H for v. That tells us that the vector of probabilities for the surfer's website at time step 1 is AS plus 1 minus A times H times W. We can take this vector of probabilities that we just calculated and we can plug it into F, and that will give us a vector of probabilities for time step 2. And that vector of probabilities for time step 2 is given by AS plus 1 minus A times AS times W plus 1 minus A squared times H times W squared. Then we'll plug that vector of probabilities into F. And that gives us a vector of probabilities for time step 3, which is AS plus 1 minus A times AS times W plus 1 minus A squared times AS times W squared plus 1 minus A cubed times H times W cubed. And this pattern continues. So for any n, the vector of probabilities for the surfer's website at time step n is 1 minus A to the n times H times W to the n plus AS times the sum from j equals 0 to n minus 1 of 1 minus A to the j times W to the j. And we can write that in a slightly simpler way by letting Q equal 1 minus A times W. So we can say the vector of probabilities for time step n is equal to H times Q to the n plus AS times the sum from j equals 0 to n minus 1 of Q to the j. Now we can look at that left term, the H times Q to the n, and we can look at what happens with it as n goes to infinity. We can use the fact that since W is a Markov matrix, all of its eigenvalues have absolute value of most 1. Since Q equals 1 minus A times W, and A is from the open interval from 0 to 1, then we know that all eigenvalues of Q have absolute value less than 1. This tells us that as n goes to infinity, Q to the n converges to the 0 matrix. This implies that H times Q to the n also converges to the 0 matrix. This tells us that the vector of probabilities at time step n, as n goes to infinity, converges to AS times the sum j equals 0 to infinity of Q to the j. Now that sum, if we take off the AS part and we just look at the sum j equals 0 to infinity of Q to the j, this sum converges because all of the eigenvalues of Q have absolute value less than 1. More specifically, it converges to the inverse of I minus Q. That tells us then that the vector of probabilities at time step n converges to AS times the inverse of I minus Q as n goes to infinity. And we can note that this has no dependence on H, the starting vector. So regardless of that starting vector H, we always get AS times I minus Q inverse as the limit of our vector of probabilities as n goes to infinity. So we still haven't answered the main question, which is why we were looking for fixed points in PageRank. So why are we looking for fixed points? Well, let's quickly look at the function that we're finding fixed points of. So that function was f of v. F of v was defined as as plus 1 minus a times v times w. And we can write that in terms of q as as plus v times q. If we're finding fixed points of that f, we're trying to solve for solutions of v for which v equals as plus v times q. We can rewrite this equation as v times the identity matrix equals as plus vq, and rearranging we get v times I minus q equals as. And I minus q is invertible, so we can solve for v and get v equals as times I minus q inverse. And we can note that this is the same vector that we see at the top of the slide. So this fixed point of the function f is the same as the vector of probabilities for the surfer's website at time step n as n goes to infinity. So the fixed point that we're finding is just the limit of the vector of probabilities. And this limit of the vector of probabilities, again, it has no dependence on the starting vector of the surfer. So wherever the surfer starts, if the surfer surfs for long enough, then their vector of probabilities for each website will get very close to as times I minus q inverse. In other words, their vector of probabilities will get very close to the fixed point of f. So this fixed point that we're finding with PageRank, it's giving us a ranking of websites, and the order of the ranking is just the order of how probable a surfer is to be at the website if they surf for long enough. And again, that ranking has no dependence on where the surfer started, so no dependence on their starting vector h. It's only going to depend on the seed vector s, the parameter a that we choose, and the internet digraph that we're using, which determines the matrix Q. And I'll mention something that I mentioned in an earlier video. The seed vector S, this can be tailored to the surfer. So whichever surfer is using the search engine, they can have a special S for them. We don't necessarily need to use the same S for multiple people. So, like I said earlier in this video, we applied PageRank to some small digraphs in one of the earlier videos. And here's a problem for you. Apply PageRank to some other digraph with any values for A and any seed vector that you choose. Thanks for watching.